In this video, we are going to complete some GCSE questions on waves. So before each question, I'm going to pause so that you can pause the video and try the question for yourself, and then I will go through the answer. So pause the video now and try parts A and B. So it asks us to calculate the speed of the microwaves by using information in the picture. It tells us the frequency of wavelengths is this. So when you see speed and frequency, you should be thinking of this relationship. Speed is frequency times by wavelength. And then we can figure out the information, the answer. So the frequency is 245, 0 and then 6 zeros. Obviously standard form would be easier to write this. If you know how to do standard form, it might be easier to write this as 2.45 times by 1, 2, 3, 4, 5, 6, 7, 8, 9. Times 10 to the 9 hertz, like that. And then what is the wavelength? Well, we've got a soft spot and another soft spot. So in a microwave, this is going to correspond to the bit of the microwave where we have a maximum amplitude of the wave, so we have maximum energy being transferred. So the true wavelength is twice what we have here. So times by twice the wavelength. So let's do the wavelength over here. So speed is frequency times wavelength. That's the symbol for wavelength. So wavelength is 41 millimeters times by 2, which is 82 millimeters. And in meters, to go from millimeters to meters, we divide by 1,000. So 82 divided by 1,000 is 0.082 meters. So times by 0.82 meters. This will equal our speed. 2.45 times 10 to the 9. If you do it in standard form, it obviously saves us having to type out all the zeros. Times by 0.082 equals 2.009 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters per second. The speed of all electromagnetic waves in air is approximately this. How far apart should the spots have been? So we basically need to do the reverse of what we've done. So speed is frequency times wavelength. We can rearrange this to say that wavelength is speed divided by frequency, which is 3 times 10 to the 8 divided by our frequency. And this will equal 2.45 times 10 to the 9, 0.1 meters. And then we said that if we halve that, we get to the answer here. So 0.1 meter over 2 is 0.05 meters. And if we wanted it in millimeters, we could times it by 1,000, but actually the answer here wants it in meters. So that is the answer. Okay, the investigation is repeated with red though. Why is the wavelength measured of the microwave different than in chocolate? So this is quite a tricky question here, because it requires you to link what's going on here to something that all waves do, which is refraction. So all waves will refract, which means that they will change their speed and therefore they will change their wavelength in a different material. So the velocity and wavelength will be different. Because of refraction in the different materials. So it's now in bread rather than chocolate. Usually we talk about glass and air and water, but here we're talking about different materials. However, still waves, they will still do the same thing. Okay, here is the next question. Pause the video now and try all of this question. So we're asked to do a couple of things. Firstly, on figure 13.2, we're asked to label a wavelength, a compression, and a rarefaction. So compression is the bits where they are close together. Rarefaction is any of the bits where they are spread out. And our wavelength is going to be from two identical points on the graph. So the easiest way to do the wavelength is to go from one compression to another compression like this. You could equally have done rarefaction to rarefaction as well. That would also be a wavelength. We then asked, use the information on these two diagrams to describe similarities and differences between these two waves, including information about how the particles move. So we've got, let's start with 13.1, the top one. What can we say? It's a transverse wave. So the oscillations of the particles are perpendicular to the direction of wave motion, or probably slightly better, energy transfer. So if the wave is moving this way, the particles are oscillating up and down like this. And in 13.2, in this figure here, this is a longitudinal wave where the particles oscillate parallel to the direction of energy transfer. So if the wave direction is this way, the particles move back and forwards like this. Now, 6-mark questions, we should always check we've done everything in the question itself. So we've done this, we've done this, we've done this, we did this, and we did this. Actually, no, we haven't done this, sorry. And we certainly haven't done this as well. So how is this wave made? We make this wave by vibrating or moving the end left and right. So we move it forward, or sort of not forward and back, left and right, and that will send the wave along. So now we've done that. Similarities and differences between these two waves. So the similarities, what do? They both transfer energy because they are both waves. You could say they both have wavelengths. That is obviously a similarity. Although it might be too obvious to get marks, but it obviously is a similarity. What about some differences? Well, the main differences are here in the direction the particles move. So I'm not doing this necessarily in the most logical way. I should really have written it all down here. But a difference is the particles oscillate differently, as explained above. So here I've explained exactly how the two sets of particles move. Okay, next question. Pause the video now and try this question. So it says, what's the difference in wavelength and amplitude between wave A and B? So let's start with A. Let's find its wavelength and its amplitude. So its wavelength is the time it takes for one complete wave or the distance it takes one complete wave to pass. So we can see we start here, we go up, we go down. This is not a complete wave. A complete wave has to go up, down, down, and up again. So we see that its wavelength is 5 centimeters. The amplitude is the maximum displacement from equilibrium, from 0. So we can see the amplitude is 1.5 centimeters for B, wavelength and amplitude. So the wavelength for B we can see is from here to here, which is 3 centimeters, and the amplitude is 1 centimeter. So importantly, it's asked for the difference. So this is not the answer. The difference in wavelength is 5 minus 3, which is 2 centimeters, and the amplitude 1.5 minus 1 is 0.5 centimeters. So it always pays to read your answer and double check the question to see that you've answered it. Okay, final question. Question 5. Pause the video now and try the first part of the question. So refraction, what is it? Refraction is when a wave changes medium. So medium means material. I guess you could also write material, but medium is usually what you write. What happens when it changes material? It changes speed or velocity. It changes direction. We can clearly see that here. The angle it's moving at is changing. And we've already said earlier, the wavelength also changes. That's probably enough for 3 marks, but it's always worth just remembering something else about refraction, that if we're going from less dense to more dense, so that's the material, so for example from air into water, then what happens, it slows down and it bends towards the normal. And the normal is the line at 90 degrees to the surface. So this here is the normal line. Pause the video now and try this question. State the law of reflection. Really easy definition. The angle of incidence equals the angle of reflection. Now, I've done this one before this question here, complete the ray diagram, because obviously knowing this is so important to answer this question. So we need to make sure that we draw with a ruler and a pencil a line that comes off at the same angle that the line comes in at. So roughly this angle here. And then obviously here it needs to reflect at the same angle that it comes in at. And then finally it needs to do the third ray. And there is a clue, obviously it should go to Alex. If it doesn't go to Alex, there's a good chance that you've done something wrong here. Okay, maybe because mirror 3 is tilted, you might have made a mistake. Now that's all we need to do for this question, but it's always worth remembering that if we have an incident ray and we have a reflected ray, what do we mean by the angle of incidence and the angle of reflection? It's not this one here. Okay, the angle of incidence is this angle and the angle of reflection is this angle. I just say that because it is relevant to this. And then finally, describe the difference between diffuse and specular reflection. So diffuse reflection is where you have a rough surface. And so when you have a rough surface, the light rays will obviously hit the bumps in slightly different places and they will bounce off in all kinds of angles, okay? So you'll get just basically a mess. If you're looking at diffuse reflection, you wouldn't be able to see your image, you'd see a blur. Specular reflection is what we usually can mean. It's this kind of reflection. It's where all of the light, when it comes in at an angle, all bounces back off or reflects off at the same angle, and then you obviously get a nice, clear image form. So a diagram would be acceptable if it was clear and labelled or explaining this in words.